Okay, got a very late start. Only because I had to deal with some pest control issue. I was doing my cardio, I was getting ready to come up on stream, and the pest control guy arrived, and I have these clover mites invading my house from my back patio lawn. Yeah, it's not fun. There's probably at least like a couple dozen clusters of them all over my house or on the exterior, and then they're kind of crawling their way into the cracks everywhere. So I had him spray for stuff. But I just learned online that they are benign and they'll die on their own, and that they're just trying to get heat because of the temperature fluctuation here. But I was kind of losing my shit because I thought they were spider mites. The pest control guy said that they were spider mites. And spider mites affect plants. And I got lots of plants. And the clover mites were on my plants, which was even more alarming. So yeah, that's why I was busy here. Okay, let's continue on with memory allocation. So we already went over the source code here. The first word is a unused padding word aligned to double word boundary. The padding is followed by a special prologue block, which is an 8-byte allocated block consisting of only a header and a footer. The prologue block is created during initialization and is never freed. Following the prologue block are 0 or more regular blocks that are created by calling malloc or free. The heap always ends with a special epilogue block, which is a 0-sized allocated block that consists of only a header. The prologue and epilogue blocks are tricks that eliminate the edge condition during coalescing. The allocator uses a single private static global variable heap list p that always points to the prologue block. As a minor optimization, we could make it to point to the next block instead of the prologue block. Okay, so we got our start of our heap. We got a prologue block, which is, so the first 3 words basically are unused, and then we got an epilogue block at the end. Okay, basic constants and macros for manipulating the free list. Figure 943 shows some basic constants and macros that we use throughout the allocator code. Lines 2 through 4, let's go ahead and just look at the code. I don't like reading textual descriptions of code. So you got some constants, you got word size, you got D size, double word size, got the chunk size. So that's what, 4K? That is our chunk size. We got a pound define for max instead of having a function. Pack a size and allocated bit into a word. So yeah, you just OR them together. And then read and write a word at address P. Get size, you end it with 7. Get alloc, you end it with 1. Given block pointer BP, compute the address of its header and footer. Header pointer, which is just -1 W size. And then The footer would be the get size on the header of the base pointer. And then you add that to the base pointer, and then you subtract 1 D size. I wonder what that is. Oh, okay, yeah, that makes sense for the header, because the header is D size in bytes. Okay, that makes sense. Yeah. Okay, let's go back to the textual description. We'll read through that now that we've read through the code. So lines 2 to 4 define some basic constants: the size of words, W size, W double words, D size, and the size of initial free block, and the default size of expanding heap chunk size. Manipulating the headers and footers in the free list can be troublesome because it demands extensive use of casting and pointer arithmetic. Thus, we find it helpful to define a small set of macros for accessing and traversing the free list. The pack macro combines a size and an allocate bit and returns a value that can be stored in a header or footer. The get macro reads and returns the word referenced by argument P. The casting here is crucial. The argument P is typically a void star pointer, which cannot be dereferenced directly. Similarly, the put macro stores val in a word pointed to by argument P. The get size and get alloc macro return the size and allocated bit respectively from the header or footer address P. The remaining macros operate on block pointers that point to the first payload byte given a block pointer BP. The header and footer macros return pointers to the block header and footer respectively. The next block and previous block macros return the block pointers of the next and previous block respectively. The macros can be composed in various ways to manipulate the free list. For example, given a pointer BP to the current block, we could use the following line of code to determine the size of the next block in memory. Cool. Creating the initial free list. Before calling mmmalloc or mmFree, the application must initialize the heap by calling mmInit function. The mmInit function gets 4 words from the memory system, and initializes them to create an empty free list. And then calls the heap extend heap function, which extends the heap by chunk size bytes and creates an initial free block. At this point, the allocator is initialized and ready to accept allocate a free request from the application. The extend heap function is invoked in 2 different circumstances: when the heap is initialized and when malloc is unable to find a suitable fit to maintain alignment. Extend heap rounds up to the requested size of the nearest multiple of 2, 8 bytes, and then request the additional heap space from the memory system. The remainder of the extend heap function, lines 12 through 17, is somewhat subtle. Let's take a look at that. So you have our init, create a initial empty heap. And then extend heap, allocate an even number of words to maintain alignment. The heap begins on a double word aligned boundary, and every call to extend heap returns a block whose size is an integral number of double words. Thus, every call to mem sbreak returns a double word aligned chunk of memory immediately following the header of the epilogue block. This header becomes the header of the new free block, line 12, and the last word of the chunk becomes a new epilogue block header. Finally, in the likely case that the previous heap was terminated by a free block, call the coalesce function to merge the two free blocks and return the block pointer of the merge blocks. Freeing and coalescing blocks, allocating blocks. I'm going to go over here. I'm going to switch over to the next lecture and see where he picks up. In advanced concepts here.
Buddy, welcome. Good to see you, and welcome to all those who are watching on videotape as well. I want to clear up. I realized after the last lecture that I didn't explain the idea of peak memory utilization very well to you, so I wanted to.
Okay, so he's picking up on explicit free lists. Just going to the size here, or slides here. Freeing with LIFO policy. There's segregated free lists. Does it get the GC? That's all an explicit list. Here's the GC stuff. Market sweep. Okay, let's finish reading this section then, and then as soon as we're done with this, just a couple more pages, that's when it gets into lecture material. So freeing and coalescing blocks. An application frees a previously allocated block by calling the mmFree function, which frees the requested block and then merges adjacent free blocks using the boundary tag coalescing technique described in 9.9.11. The code of coalesce helper function is straightforward. Implementation of the four cases outlined in figure 940. There's one somewhat subtle aspect. The free list format we have chosen with its prologue and epilogue blocks that are always marked as allocated allow us to ignore the potentially troublesome edge condition. Jesus Christ. Troublesome edge condition where the requested block BP is at the beginning or end of the heap. Without these special blocks, the code would be messier, more error prone, and slower because we would have to check for these rare edge conditions on each and every free request. Allocating blocks. An application requests a block of size bytes of memory by calling the malloc function. After checking for spurious requests, the allocator must adjust the requested block size to allow room for the header and footer and to satisfy double word alignment requirements. Lines 12 to 13 enforce the minimum block size of 16 bytes, 8 bytes to satisfy the alignment requirement, and 8 more bytes for the overhead of the header and footer. For requests over 8 bytes, the general rule is to add in the overhead bytes and then round up to the nearest multiple of 8. Once the allocator has adjusted the requested size, it searches the free list for a suitable free block. If there's a fit, then the allocator places the requested block and optionally splits the excess and returns the address of the newly allocated block. If the allocator cannot find a fit, it extends the heap with a new free block, places the requested block in the new free block, optionally splitting the block, and then returns a pointer to the newly allocated block. This is all code. This is implementation, implement a place function. I'm not doing that. Okay. So now we're on explicit free lists. We decline to do 98 and 99. So let's vim up problems. Okay, let's get on to the lecture then.
Explain that. It's an important idea, and I want to make sure that we have it clear. So if you recall from, we're executing a sequence of requests, R0, R1, R2, RK up to Rn minus 1. And at any point in time after k plus 1 requests, we have hk, which is the heap size, after k plus 1 requests. Then we have pk, which is the aggregate, the sum of all of the payloads after k plus 1 requests. Okay, so what we're trying to do with this pk measure, this aggregate payload, is at any point in time, so as we execute requests one after the other, the sum of all the payloads in the heap is going to increase or decrease, right? So if we execute an allocate, then the size of the payloads will increase. If we execute a free, the size of all those allocated payloads will decrease. Right? So as we're executing this sequence of requests, the aggregate, the sum of all the payloads is going to be increasing and decreasing. Okay? And so what we're capturing with the sum of all these payloads is like a perfect allocator that has no overheads, and even more so, one that we can, where we're allowed to compact blocks. So the sum of all of the payloads is the minimum possible heap size, or it's the minimum possible number of bytes required by those allocated blocks. Okay, so it's very, very aggressive, and it's impossible to achieve. But we're going to use that as sort of our best case. Okay, and so to measure peak memory utilization after k plus 1 requests, which will denote U of k, that's going to be equal to the max for all I less than or equal to k of our aggregate payloads divided by the size of the heap after k plus 1 requests. Okay, so what we're doing with this max is we're remembering the high water mark. You know, as our aggregate payloads increase and decrease, we're remembering the high water mark. Okay, so that was sort of the worst. That was like the biggest set of payloads that we had. And then, so the max is remembering that high water mark, and then we're dividing by the total size of the heap in order to get an efficiency measure. Okay, so this max pk is kind of, this is the best we could have done divided by the total heap size. Okay, so yes. Well, the allocator keeps track of how big the heap is, so that's pretty easy, right? So every time it calls sbreak, it just that adds to the size of the heap. And remember, we're assuming that the heap in this case is always increasing. Okay, so, but even if we allow the heap size to decrease, you could just if the allocator is controlling the size of the heap by calls to sbreak. Okay, so is that clear? So for UK, the higher the better. Okay, and for any sequence of allocates and frees, this max pk will be the same. Okay, that's constant, right? But what varies is h of k, and that depends on how efficient your allocator is using the heap storage. Okay, yes, question? So what we're doing is, at any point in time, after k plus 1 requests, we're evaluating the utilization of our heap up till that point. So it should be k.
I mean the max I is more than or equal to k. Then
for I less than or equal to k. Oh, I'm sorry. Yeah, sorry. Good catch. So that should be an I, right? We want to look at for all the requests that came before. Okay. Any other questions? So just saying, that was we're vital to peak memory utilization after k plus 1 requests, which will denote U of k. That's going to be equal to the max for all I less than or equal to k of our aggregate payloads divided by the size of the heap after k plus 1 requests. Okay, so what we're doing with this max is we're remembering the high water mark. You know, as our aggregate payloads increase and decrease, we're remembering the high water mark. Right? So that was sort of the worst. That was like the biggest set of payloads that we had. And then, so the max is remembering that high water mark, and then we're dividing by the total size of the heap in order to get an efficiency measure. Okay, so this max pk is kind of, this is the best we could have done divided by the total heap size. Okay, so yes. Well, the allocator keeps track of how big the heap is, so that's pretty easy, right? So every time it calls sbreak, it just that adds to the size of the heap. And remember, we're assuming that the heap in this case is always increasing. Okay, so, but even if we allow the heap size to decrease, you could just if the allocator is controlling the size of the heap by calls to sbreak. Okay, so is that clear? So for UK, the higher the better. Okay, and for any sequence of allocates and frees, this max pk will be the same. Okay, that's constant, right? But what varies is h of k, and that depends on how efficient your allocator is using the heap storage. Okay, yes, question? So what we're doing is, at any point in time, after k plus 1 requests, we're evaluating the utilization of our heap up till that point. So it should be k.
I mean the max I is more than or equal to k. Then
for I less than or equal to k. Oh, I'm sorry. Yeah, sorry. Good catch. So that should be an I, right? We want to look at for all the requests that came before. Okay. Any other questions? Okay. All right. So last time we looked at some simple the basics of dynamic storage allocators, and today we're going to look at some more sophisticated techniques using different data structures to store the free list primarily. We'll look at implicit allocators, so we'll get a sort of a brief survey of how garbage collectors work, and we'll just look at one, just one very simple kind of garbage collector, but it'll give you an idea of what that means. And then we'll finish up. We'll finish up by looking at all the ways you can get yourself into trouble by using dynamically allocated storage. So once you start dynamically allocating storage, things can go really bad really quickly. And so we'll go over some of those bad things that can happen and try to alert you to those so you don't do them in your programs. Okay, so we looked at how to store a free list in this sort of implicit form by just walking the entire heap and thereby sort of being able to visit all the free blocks. But we can do better if we actually have if we store the free list as a doubly linked list. So we call these explicit free lists. So the idea with an explicit free list is that we put pointers, we put the pointers that implement the doubly linked list inside the body of a free block, so where the old payload used to go. So allocated blocks look exactly the same as they did before, right? There's a header, boundary tag, optional boundary tag footer, and then the payload and any padding. Free blocks, though, the allocator is not allowed to touch anything inside the payload of an allocated block. But free blocks are free, right? Nobody's using them, and so the allocator can put the pointers that implement the data structure inside what was the old payload. So logically, this is just a simple doubly linked list that you've all seen before. But actually, these things can be anywhere in memory, right? And so here we have a block of size 6, and it has a forward pointer that points to some other link, and it has a backwards pointer that points to this block, which happens to have a greater memory address than it. Okay. So just the idea is that you can't, unless you go to great pains to maintain this sort of address-ordered structure, these blocks can be sort of scattered anywhere in memory.
So this happening after several times of malloc?
Oh yeah, so this is after several, just sort of indefinite number of mallocs and frees. And yes?
What if you were to free a block that was between two free blocks?
Oh yeah, good question. So the question is, what would happen if you freed a block that was in between two free blocks? And so you have to coalesce. It gets a little tricky, and I'll show you in a second. It'll be good. Now allocating. Oh yes, questions.
So what happens with locality in a free block?
So the question is, what happens with locality? So you still get block locality. These blocks are still contiguous. So if you're scanning sort of a set of allocated blocks, it would be better if you could keep them all contiguous, right? So that's really, and so there's a, that's a trade-off. It gets difficult if you think, how can you maintain? So you don't really care about the locality of free blocks, right? You're just walking a linked list. Well, no, I shouldn't say that. If you're walking that list, if you hit one free block, it would bring in a whole page. So it'd be better if you were walking, if the list, if as much of that list was contained within that page. So you could benefit with both allocated blocks because applications would be using them, and with free blocks because the allocator would be walking that free list. So, question?
Would it make sense to kind of have the programs that have implementation to your allocators for free break? So even though say you only allocate into a couple of small structure, if you know that you can allocate out of them, somehow pass information so that the allocator learns that you're going to try to allocate a couple of allocators.
That's a really good question. So the question is, would it be possible for an application to sort of give hints to the allocator that would improve the allocator's performance or memory utilization? The answer, you absolutely could. But if you did, it wouldn't be a general purpose allocator. So like malloc is a general purpose allocator. So it provides there's no option. It doesn't provide any arguments in its interface for passing that information in. But it absolutely, if it had some knowledge about the future behavior of a program, it could benefit, right? So especially consider, you always have this decision when you place an allocated block, whether to split that block or not. Well, if you knew that you were going to get a request, if you split that block and you knew that you were going to get requests coming in the future for sizes of the original block, then you wouldn't want to split it, because then you would just keep it unsplit, and then when you freed it, then you'd have a block that would be the right size for that future request. And so you can absolutely benefit from that. And so although you can't, general purpose allocators, there's no provision for that kind of hinting, but there's nothing to prevent an allocator from doing predictions based on the previous pattern of requests. So if you're getting a pattern of requests that's alternating large block, small block, large block, small block, you could exploit that. Maybe predict that the next request will be for if the previous request was for a large block, the next one might be for a small block, and you could. That's a good question. Any other questions? Yes. I don't know. So the question is, are there intelligent allocators that do that kind of prediction? And if there are, I don't know them, but I wouldn't say no. Yes.
As a more general question, using this sort of method to decide that you track the size and such, what would happen if you end up with a free block that's a block, just like in the middle of two allocated blocks, just a single block?
Oh, so the question is, what if you ended up with a free block that's a single block surrounded by two allocated blocks? Well, in fact, that's one of the invariants that a good allocator has to maintain. You should never have two contiguous free blocks, right? The allocator should always be coalescing as much as it can. And if it does that coalescing, if it always does that coalescing, then there will never be two contiguous free blocks. Okay. Yes, question?
What's the advantage to doubly linked list rather than singly linked?
Oh, you'll see when it comes into play when we free a block, because you have to sort of stitch up. When you free a block, you have to sort of stitch up the linked list, and so you need both pointers. You can do it with singly linked lists. So in the K&R book, there's an allocator that uses a singly linked list, but the disadvantage is that free requires a search, so it requires a search from the beginning of the list to find the previous block. Okay. Any other questions? These are good. Yes, question.
For memory utilization, how does the header and footer count towards memory utilization?
Okay, so the question is, for memory utilization, how does the header and footer count towards memory utilization? And so those are overhead that decrease memory utilization, okay, because they're not payload. So when we're computing memory utilization, we're using the payload, the aggregate payload, to estimate our utilization or to compute our utilization. So anything that's not payload is overhead.
Okay, so we have word and everything when allocated was also one word, then we would have 50% regularity?
So if all of our payloads were one word and our overhead was one word, then there'd be 50%. Yes?
If you have the book as pointers to next to previous block, you still need like the footer, like boundary tag?
Yeah, so the question is, do you still need a boundary tag if you have these next and previous pointers? And the answer is yes, absolutely. And you'll see in a second why. Yes?
So if you have pointers from next to previous, you have to, if you want to allocate a small amount of space, then it would take to have pointers, you have to allocate a larger amount of space.
Okay, that's a really good question. So what do you do if you have next and previous pointers? What happens if there's a request for a smaller block? So the answer is that all of those things, the header, the footer, the next and previous pointers, impose a minimum block size. So if you have a one-word header, one-word footer, one-word prev, and one-word next, then your minimum block size is 4 bytes, and that would be with a zero size payload. So you can never allocate a block smaller than your minimum block size. So it's a very good question. So it makes a difference, right? Even though we're, it looks like we're getting these pointers here for free, but we're not really because of this minimum block size requirement. Yes?
So is there a way to, going back to the idea of like locality, is there a way to force to allocate a gigantic block and then force out to give you specific parts of that? So say you want, say you want to allocate 100 structs, and you allocate the side 100 structs and say each of, or I guess one back structs, so that's right? But if you wanted to like take first half, take them structs, and take second half, take an insert or something, and if you say all this stuff my program should be contiguous, like separate heap, so it's like you're explicitly asking for that one gigantic block and split it off.
Yeah, okay, so the question is, can you just get one large block and then split it up? And I guess you're assuming that the request would be for equally sized objects, right? So this, and that's a really good strategy, actually. So if you know, or if you think that your workload is going to have, now you can't do this in general purpose allocators, but for like a special purpose allocator, if you know that you're going to be asking for objects that are all the same size, like compilers, for example, maintain abstract syntax trees, and they're allocating nodes dynamically, and those nodes are the same size. So if you can exploit that by just allocating a large chunk, and then allocating all the objects of that size out of that chunk. It's very efficient. You don't even need pointers or anything. All you need is a bit vector to tell you which chunks are allocated and which chunks are free. And you also, as a side effect, you'll get that contiguous access. So if a program accessed those objects, like to be part of a linked list or something that it was going to traverse, you could allocate those in order and contiguously. Now with a general purpose allocator where you don't really know what's going to be requested, it's
generally, the same program, they're probably going to allocate some small stuff. So you can code vectors and small things.
absolutely you could do that. You can make general assumptions about the sort of behavior of your programs, and you could run traces, or like in the case of malloc, you could look at the traces. But that's a really good thing. You can't just like do if statements to say, well, if the size is 42 and then the next size is 24, then I know it's this trace. But you can look at a trace and say, there's an interesting pattern here. I'm going to account for that pattern. I'm going to optimize for that. That would just, and that's perfectly valid. That's just like taking advantage of your workload, right? That's what we do in systems all the time. Size is 42. It's
generally, the same program, they're probably going to allocate some small stuff. So you can code vectors and small things.
absolutely you could do that. You can make general assumptions about the sort of behavior of your programs, and you could run traces, or like in the case of malloc, you could look at the traces. But that's a really good thing. You can't just like do if statements to say, well, if the size is 42 and then the next size is 24, then I know it's this trace. But you can look at a trace and say, there's an interesting pattern here. I'm going to account for that pattern. I'm going to optimize for that pattern. And that would just, and that's perfectly valid. That's just like taking advantage of your workload, right? That's what we do in systems all the time. Yes?
So say we have a large payload that we need to allocate, but can we divide it up and at the end of the first part of that payload, just have a pointer to the remaining part of the payload which is stored in some other part of the heap?
Oh, so the question is, why can't we sort of have separate areas of the heap for the pointers and the payloads, right?
So how about we split up the payload and then join them up with pointers, like not have them contiguous?
Oh, well, why not? Okay, so the question is, why can't we split up payloads and link them together with pointers? The answer is that the application is expecting a contiguous block. Allocator can't put anything in the payload. Right? All it's allowed to do is return a contiguous block of the size that the application requested. And once it does that, it can't touch it. Okay. All right, good. All right, so let's look at how we allocate in free. If we have this explicit list, how we would allocate in free blocks. So allocating is pretty simple. We'll have, so here's our sort of a graphic of our free list. And so we have forward pointers and backward pointers. And the idea is we want to allocate out of this middle block. So we allocate the block of the size that we need. And then we just update the forward and back pointers of the previous and next blocks to point to this new free block. Okay, so that's pretty simple. We're updating 1, 2, 3, 4, 5, 6 pointers. Okay. You know, it gets trickier when we have to free because we require coalescing. So when you free a block that was previously allocated, the question is, what do you do with that free block? Right? It wasn't in the free list because it was an allocated block. So now that you freed the block, where do you put it? Right? You've got to put it somewhere. So the simplest thing is this LIFO policy. So the simplest thing is just put it at the beginning of the list. So the last block freed is the first block allocated if it fits. Okay, so that's so-called LIFO. Now this is simple because you're always doing the same thing. You're just putting the block at the beginning of the list. And it's constant time. You're just updating a few pointers. Okay? But the studies suggest that the fragmentation can be worse than the alternative technique, which is to keep the blocks ordered by address. Okay, so if you choose this address ordered policy, when you free an allocated block, you're going to somehow place that block in the list so that the previous block begins at a smaller address and the next block begins at a larger address. Right, so this generally involves some kind of search. Right? You're just given this allocated block, and then somehow and you know its address, and so now you've got to somehow search the free list to find the proper place to insert it. Now I suppose you could do better if you had some kind of, so if you could speed up that search with some kind of balanced tree, that would be one option. Right? But then the problem we always run into with balanced trees, and usually one student, at least somebody always tries to implement malloc with some kind of balanced tree, red-black tree or something, and it seems like a really good idea, but you have to realize that you're competing with other techniques, specifically segregated lists, that are very fast, that have very small constant factors. And even though ordered lists are, I think, it's usually n log n to update an ordered tree, a binary ordered tree, the constant factors can be quite large. And so you usually get nailed up with the constant factors of maintaining the tree. And you don't get help that the search time is log n. But as we'll see with segregated lists, in the limit, as the number of different size classes increases, the search time approaches constant time. And if you have size classes that cover ranges of powers of 2, then the search time reduces to log time anyway, because the size of each class is sort of now logarithmic, the log. So I would suggest just doing the simple thing. Usually whenever you're dealt with sort of large design space like malloc, you're better off doing the simple thing, and then optimizing only when you see that you need to optimize. Okay, so remember last time we talked about this trick to eliminate the boundary tag footer and allocated blocks. That's an example of an optimization you should defer, so that do the simple thing, and then try to improve incrementally by this optimization or another optimization. So there's this phenomenon. A lot of programmers make the mistake of what we call premature optimization. So they try to think of all the fancy things they can do, and then they put all those in at the beginning, and before they even know that it needs to be optimized. Okay, so the way you want to work on this in any sort of complex problem like an allocator is to first do fairly simple things, and then look and see where the slowdowns are, your inefficiencies are, and then just sort of hit those one after the other and optimize only for the things that are necessary. And this is a good example of that. Okay, now to get to your question about freeing. Freeing is tough because we always have to do this coalescing, right? Because of this invariant that we can never have two free blocks, two adjacent free blocks. So let's go through each of those 4 cases that we went over last time and see how we would do it now that we have this explicit free list. So here we have the root of our free list pointing to the first block in the free list. There's a null back pointer, and then there's a null pre-pointer, and then the next pointer points to some unspecified block. And so we have this yellow block which is allocated, and now the application is called free with a pointer that points to the beginning of this block. So what do we do? Well, this case is pretty simple because there's no coalescing because both the predecessor and successor blocks are allocated. Okay, so this newly free block now becomes, we're going to do a LIFO policy, so this becomes the first block in the free list. And so we update the root to point to this newly free block, and we update the forward pointer of that block to point to what used to be the first block in the heap. Now I'm going to be careful. It's a little bit confusing because we've got sort of 2 notions of the previous and next, right? There's the, given some block, there's the predecessor block in memory, which may or may not be allocated or free, right? It may or may not be in a free list. And there's a successor block. Okay, so we'll use predecessor and successor to distinguish adjacency in memory. Okay, and we'll use prev and next to denote adjacency in the free list. Okay, so this block is the next block for the current block, and it has no previous block. Okay. All right, now what about case 2? Remember case 2, the predecessor block is free, and the successor block is allocated. And now we want to free what was an allocated block, denoted by yellow. And we have that this predecessor block is part of the free list, right? So it has previous and next blocks that are just part of the free list. Right? So our root points to the first block in the list, and then eventually you get to this free block, which points to this free block, which points to this free block. Okay, so what we have to do then is we have to coalesce these two blocks into one big free block. Okay, and then we have to splice it out and stick it at the beginning of the list. Okay, so what that looks like conceptually is we coalesce these 2 blocks now to form this one free block, and then we splice it out by having what was its previous block now point to what used to be the next block, okay, of the current block. Okay, so the pointer from this block now points to this block. Okay, and then so we've effectively spliced that current block out of the free list, and then we have the root point to that block, so that's now the new first block in the list. Okay, and then we have to update what used to be the first block in the list, so now it points back to the newly freed coalesced block. So is that clear to everybody? Yes?
So would the root be a global variable?
So would the root be a global variable? It could be, or it could be. There's 2 ways to do this, right? It could just be a global variable, or it could be a struct that of like previous and next pointers. So sometimes it's easier if you keep the same. When you do an unlinked list, the root, if you just make it the same as all the other nodes, it can simplify things. But yeah, it could be a global variable, global scalar in the allocator. Okay, so now one thing that comes to mind, there is an optimization that we could do. In this case, do you see when we coalesce, we could just leave that block right there in the free list. Right? Although we've adopted, so the examples I'm going to show you are assuming a LIFO policy for insertion. We could just leave it there, right? And just don't coalesced block, and then we don't require, in this case, we wouldn't require any free list manipulation. Okay, but that would be one of these optimizations, right? Now, case 3, if you recall, is the case where the predecessor block is allocated and the successor block is free. The successor block is free. So in this case, what we have to do is we have to coalesce the newly free block with the successor block, and then we have to splice it out in just the same way we did in case 2. So we splice it out of the list, and then put it at the beginning of the list by pointing the root at it, and then updating what used to be the first block in the list, updating its back pointer, its pre-pointer to point to this newly coalesced block. Okay, so this is completely symmetric with the case that we looked at before, but now we no longer have, it's a little bit trickier. If we just wanted to leave this block in the free list, we'd have to update all these pointers to point back to the beginning of the newly created block. Okay, so there's, so in this case, there's no performance optimization, right? We're still updating the same number of pointers, whether we put it in the beginning of the list or if we splice or if we leave it there. Okay, and now case 4 is that's the case where both the predecessor and successor blocks are free. So we have to apply the same splicing technique to both the predecessor block. We have to create this new coalesced block, and then we have to splice. We have to sort of splice it out by updating 2 different sets of previous and successor blocks. Okay. So when we're finished with that, this newly coalesced block now is the first block in the heap, in the free list, and we spliced it out from these 2 different parts of the free list. Okay. So any questions about this? Is where you really it looks really simple to do, but I guarantee you this will be some of the hardest. It's only like 200 lines of code, but some of the hardest code you'll have to write because you're sort of free of the C's type system. You have to do everything by explicitly casting. These pointers are just in the middle of arbitrary blocks. And so it looks simple with the diagram, but you're going to have to be really careful when you do this. In fact, what I would suggest, the best suggestion I can give you is to start with the implicit list allocator that we described in the book, which is too slow to get any credit. It's a terrible allocator, but it contains all the basic ideas. And then write a function called insert block and write another function called remove block that inserts a block into the free list and removes a block from the free list, respectively. And if you abstract it like that, if you use that kind of abstraction, it's pretty simple to convert the implicit list allocator to an explicit list allocator. Okay. It'll still be too slow to get, so that'll go from like an F allocator to a B minus allocator. And then to really make a good allocator, like an A allocator, you need to use segregated lists, which we'll look at in a second. Okay, so the explicit list, now the allocation time is linear in the number of free blocks instead of the total size of the heap. So this is much faster when you have a lot of allocated blocks. It's a little more complicated because of all this splicing business, and you do need some extra space in your for these pointers, which increases the minimum block size and creates additional overhead. Now, the linked list, the explicit list allocators aren't really efficient enough to be used for sort of general purpose real life allocator, but they are useful as part of a segregated list allocator. So you can have multiple free lists, each of which is an explicit list, and it's fine for that application. All right, so let's look at our third method, which is to create what we call a segregated free list, which is to have multiple free lists with different size classes. So the idea is that each class of sizes, block sizes, has its own free list, and that class can be singletons, maybe of one particular size, or it can be a range of sizes. So you might have a number of different, if your workload consists of a lot of these small blocks, and you know that there's going to be a lot of requests for blocks of 1 through 4, you can have different free lists for those small block sizes, and then after that you can go and just do ranges of power of 2. So that's a common technique. So here we have a size class that covers blocks from size 5 to 8, and then another size class that covers everything else. So the idea with a seg list allocator is that, so given an array of these free lists, each one for some size class, if we want to allocate a block of size n, then we go to the appropriate free list. Right? There's always going to be one free list for any n, and then we search that list just like we did before for some size, a block size m greater than n, and then if we find it, then we place the new block, we place the block in the block that we found, we split it, and we take the split block and we put it into the appropriate size class, right? So that the block that we split off may or may not belong to the current size class anymore. Right? So we may have to move it and insert it into whatever the appropriate size class is. If there's no block, if we can't find a block, then we have to try the next larger size class. Okay, so it's possible for a given size class there might not be a block that fits. So we just have to, we go to the next size, we try the next larger class, and chances are we'll find a block that fits there. And you keep doing that until eventually, if you can't find it, you're eventually looking in the size class that covers all the rest, the last size class. And if then you can't find it, then the allocator has to allocate more memory by calling sbreak. Okay, to free a block, you coalesce like before, and then you place it on the appropriate list. So that's straightforward. And again, you have this option to try to maintain the list address order, or just do the simple thing and put it at the beginning of the list. Okay, so seg list allocators are by far the best type of allocator because they offer you improvements in both performance, throughput, and memory utilization. So they're faster, they have higher throughputs because the individual size classes are smaller than just like the one giant free list. But also you're searching, you know that the list that you're searching is going to be close to the size that you're looking for. So the chances of finding something quickly in that particular size class are higher than they are if you're just searching a single free list that holds all different size classes. Okay, so search is faster, so that increases throughput. But the big thing about seg list allocators is that, like we talked about before, they approximate best fit without sacrificing performance. Right? Before, if we wanted to do best fit on a free list, we had to search the whole free list and then choose the block that fit the best. In this case, we get best fit for free by virtue of having these size classes. Okay. And so this is, this is how you can improve your memory utilization. Yes?
It's great function time. So, for example, if we run out of space in our heap, should we just allocate n more bytes, or should we allocate a bit more to that next time?
Oh, yeah, good question. So the question is break constant time? It is, but it's very expensive. So it's a syscall, so it has to pass from user space into the kernel. That involves changing contexts, changing stacks. So syscalls, generally, you can count on a syscall being like several hundred microseconds. Okay, it's a non-trivial overhead. And so in that case, you wouldn't want, you want to amortize the cost of the break by allocating a somewhat larger chunk. But you have to be careful. If you allocate too large of a chunk, then your memory utilization goes down. So it's a trade-off. It's another one of these space-time trade-offs. Question?
Where do you store this array of free lists?
So where do you store this array of free lists? So you store it in the beginning of the heap. Yeah, in fact, for your malloc lab, we require you to do that. We don't know. And the reason is we can't. That array affects, in some small part, depending on how large that array is, it affects your memory utilization. And so it should be at the beginning of the heap. Okay, there's allocators have been around forever, and the classic reference is Knuth's 1973 text. And there's also this great paper which you can get from the book's website from 1995 that does a survey of dozens and dozens of techniques. We're just scratching the surface here. that paper is a fascinating read, and it may give you some ideas for your lab. Okay, now so far, we're assuming that the application is responsible for both allocating storage and freeing storage. But there are a form of memory managers called implicit memory managers that do the freeing for you. So applications allocate space, but they never have to worry about freeing space. The system does that automatically. And so the idea is to identify so-called garbage, so areas of memory that can never be referenced anymore, and then free up those blocks. Okay. So what's garbage? Well, here's an example. We have a function foo that mallocs 128 bytes and stores the address in this pointer p. And then at some point, when it returns from foo, this pointer is lost forever, right? Because p is a local variable on the stack. So once this function returns, the block of memory pointed to by p is garbage. It can never be referenced again, because there's no way for the program to get access to that. And so an allocator will recognize at some point that this block of memory is garbage, and then it'll free those blocks by calling free. It's the same exactly the same free call as we've discussed, but now it's called by the garbage collector, not by the application. Okay, so you see this in all different kinds of dynamic languages, and there's also variants available for C, but because of C's pointer properties, that the garbage collectors for C are conservative in the sense that there's some blocks won't be freed. There's some garbage blocks that won't be freed because the allocator can't determine that they are indeed garbage. So it has to be careful. Whenever there's a doubt, it doesn't reclaim the allocated block. So it gets to this question of like, how does the memory manager know when memory can be freed? And if somehow we knew, we could predict all of the future requests, and then if we knew that there were no future requests access that block, then we could free it. Okay, but we can't predict that. Okay, so we have to. But if there's no pointers, if no pointers exist to a particular block, then we know that it can't be accessed. Okay, and so that we can predict. Right? If there's some way we can sort of scan the program, scan the memory, identify all the pointers in that memory, and see which blocks are pointed to, and if they're not pointed to by any pointer, then they're garbage by definition. Okay, so to do this though, it's difficult. So first of all, the memory manager has to be able to distinguish pointers from non-pointers, which we can't do in C, right? They're just these integral values, right? We don't know. It could be we see this large integral value, this large long 8-byte value. It could be pointing to a data structure, or it could just be a large integer. Right? We don't know. And then all pointers have to point to the start of a block, which is not true in C either. Okay, so if we have a pointer and we identify that it's a pointer, then we know that it points to some block. If it points inside of a block, how do we find the beginning of that block? How do we know how big that block is? Right, so it has to point to the beginning of the block where the header tells us the size. And there can't be a way to hide pointers. So the property of being a pointer has to be some kind of static thing that can't change. So that's sort of the challenges if you think about how in the world can you implement a garbage collector. So those are some of the challenges that they present. And because of that, this has been the history of research in garbage collectors is old, it's ancient, and ongoing. It's still ongoing today, particularly in the context of parallel programs and garbage collecting programs that are running multiple threads. So there's a whole bunch of these things that people have looked at going all the way back to 1960. Today we'll look at the simplest, one of the simpler variants called mark and sweep, and we won't discuss the rest. But if you're interested in them, there's a pretty good book that describes these things. All right, so how do we build an allocator? So we start by viewing memory as a directed graph, where each node in the graph corresponds to a block. Okay, a heap block, and an allocated heap block. And each edge is a pointer that's contained somewhere within that block, a pointer to another block. And then there's special nodes called root nodes that contain pointers into the heap, but they're not part of the heap. So for example, pointers that are stored on the stack, pointers that are stored in registers, they point to memory locations in the heap, but nothing. But they're outside of the heap, and we call those root nodes. So nothing points to them, or at least if something does point to them, we don't care about what it is. Okay, we're only concerned about characterizing nodes that correspond to memory in the heap. So we say that a node or a block is reachable if there's some path from a root node to that block. So, and we've denoted those by green. So all of these green blocks in the heap are reachable because you can start at a root node and just follow some sequence of pointers to get to that node. Okay. Nodes that aren't reachable are garbage because there's no way to get to them from the root nodes. Okay, so there's no node inside the heap that points to them, and there's no root node that points to them. So basically, there's just no path from a root node that'll get you to one of these non-reachable or garbage nodes. And since they're non-reachable, the application will never be able to reference them in the future. So we can predict with certainty that those are garbage and they can be freed. Okay? So basically, after we free these, then they're removed from the graph. So now we can build a simple garbage collector on top of the existing malloc and free package. Right? So you implement malloc and free just like before, and then the program calls malloc just like before, and you do malloc exactly the same way until you run out of space by whatever definition you want to use of running out of space. Maybe you have some kind of maximum heap size you're willing to use, or at some point the OS will just stop giving you virtual memory. When you run out of space, you add an extra mark bit into the header of each block. So this could be, we have like 3 or 4 spare bits that we can use in the header. So we can denote one of those as the mark bit. And then our garbage collection phase, when we run out of space, consists of two different subphases. One is the mark phase, which starts at all the roots, and it just traverses this from the roots. It traverses the set of nodes that are reachable from the root, and it sets the mark bit in each one of those nodes. Okay. And then after you finish marking all of the reachable blocks, then you sweep through the entire heap, starting at the very beginning of the heap, and you look for all allocated blocks that aren't marked. Okay, because if they're not marked, they're not reachable and they're garbage. Okay. So you do this. So you sort of do you do a search from the roots, and then you do a sweep of the entire heap. So let's say before the marks phase, we have a heap that looks like this. We have a single root that points to this block. And what we're going to do here, we're always going to point to the payload, right, of the block. It's just a convention that we use. So we're pointing to the beginning of the block because we know that the header is one word behind it. And so let's say, and in this case, the edges denote pointers that are contained in the block. So they're not the previous and next pointers that we're maintaining. These are just pointers that the application has put into those blocks. So here we have the root pointing to this central block, and then there's a pointer that points to this block, and there's another pointer that points to this block, and there's a pointer in this block that points to this block. So after we do the mark and we search these blocks, then all of the reachable blocks have the mark bit set, which is denoted by pink. And so then you see, and then the blocks that aren't marked, then we can free and return to the free list. Okay, so let's look at the assumptions for a simple implementation just to make sure this is clear. So the application calls new to get a pointer to a block with all the values cleared. It calls read bi to read location I of block B, and it uses write biv to write a value v into location I of block B. And then each block will have a header word which will address as b of -1. And then the garbage collector has functions that it uses to identify whether its input parameter is indeed a pointer. Okay, so there's some way to distinguish a pointer from a non-pointer. And it can get the length of some block, not including the header, and it can get a set of all of the roots. So given those assumptions, our pseudocode for the mark step, it takes, so this initially is a pointer, a root pointer. Okay. And then we check, as our terminating condition, we check to see if that input is indeed a pointer, and if so, we return. Okay. And then we do a depth first reversal of the graph. So so we're doing a depth first reversal of the graph, and this pointer is sort of a terminating condition for that depth first reversal. Then we check the mark bit, and if it's set, then that's another terminating condition. There's no reason to search. Once we find a marked node, we know that everything reachable from that node is marked, so we can terminate or return and just stop the search. If it's not set, then we set the mark bit, and then we look at each word in the block, and we recursively call mark on each one of those words. Now, each one of those words may or may not be a pointer, right? So if it's not a pointer, then mark will just return instantly, immediately. If it is a pointer, then it will continue the recursive depth first search. Okay, so does that make sense? It's just the familiar depth first graph traversal that we all know about. Okay, and then the sweep. Sweep takes a pointer to the beginning of the heap. It takes a pointer to the first block in the heap, and then a pointer to the end of the heap. And then in a while loop, then it scans the heap, each block. If the mark bit is set, it clears it. If it's allocated, it frees it, right? And then it updates, and then it gets the address of the next block, and then just continues until the end. Okay, so how do we do such a thing in C, right? Because all of these assumptions I made don't hold in C, right? You can't tell a pointer from a non-pointer. Pointers can point anywhere. So what you could do, so the big issue is that if we get some value, even if it is a pointer, it could point right into the middle of the block. So given that, so first of all, we don't know if that value really is a pointer. It could just be a big integer. But it also could be a pointer that's pointing into some data structure. So if it is a pointer, how do we find the beginning of the block? So what we could do is just assume that every value is a pointer, and then we maintain a balanced tree to keep track of all the allocated blocks. And so whenever we encounter a particular value, we would search that binary tree to see if assuming it is a pointer, if it falls within the beginning and end of some allocated block. Okay? If that condition is true, then we assume that it's pointing that's a pointer to an allocated block, and we assume that that block is reachable. Now the reason it's conservative is because it really may not be a pointer, it might be this integer, and we'll assume it's a pointer and assume that the block that it purportedly points to is allocated. But it may in fact not be a pointer, and the block that it points to is garbage. Right? So with this scheme, we would leave some non-reachable blocks. We would indicate that some non-reachable blocks are really reachable. Okay, so now that we've got this great tool to dynamically allocate memory, we can use it in our programs and shoot ourselves in the foot in all different kinds of ways. Okay, so I'm gonna try to help you out here by identifying some of the perils and pitfalls that we can run into with memory-related operations or operations on memory. And errors involving memory are the worst kinds of bugs to try to find out. And the reason is that they're distant in both space and time. So let's say you write to the wrong memory location and corrupt some data structure. The write doesn't elicit any error. You only find out about that erroneous write when you try to reference that data structure or that particular part of the data structure, which may be a part of the code that's way far away from the write that caused the problem. Both in space, in distance, lines of code, it could be a completely different function and a completely different module. But also in time, it may not, you may do the write, and then eons later, there's some read and it fails. Right? So this is a fundamental thing that makes memory-related bugs just so nasty. And another thing that makes them hard to deal with is people's misunderstanding and misuse of pointers. Right? So usually an erroneous write is some either a misunderstanding of pointers or an improperly initialized pointer. So it all boils down to these pointers. Okay? And so I'm going to show you how to understand pointers. Okay? For the first time in your lives. I don't know about you, but when I learned C, I learned about pointers. I just knew about what a few different types of pointers were, and I did it by pattern matching. So I knew that int star p was a pointer to an int. I knew that int star star p was an array. I knew that int star p open bracket close bracket was also an array, just a different way to express that array. So I had a small handful of pointer types that I could deal with, but I had no underlying understanding of what that meant or anything. It was just pure pattern matching. And I'll bet you that's the way you do it too. All right, but that's all going to change today. All right, so in order to really understand pointers, you need to understand the precedence of various operators in C, because the pointer types are declared using these operators. And so my copy of KNR has a dog ear to page 53. So this table comes from page 53 of KNR, and you should have a paper clip or have that folded over for reference. Now the thing to notice is that function and array and these various struct operators have the highest priority, highest precedence, and then that's followed by unary operators. So the star, this is the dereference operator, and then the address of operator. They fall right below the highest precedence operators, and then the binary versions of operators, that you use in arithmetic operations are below those. Okay, so just remember that function and array is higher than star. Okay, the dereference. That highest in priority, highest priority. All right, so in order to really understand alpha array, I knew that int star p open bracket close bracket was also an array. What that meant or anything, it was just pure pattern matching. And I'll bet you that's the way you do it too. All right, but that's all going to change today. All right, so in order to really understand pointers, you need to understand the precedence of various operators in C, because the pointer types are declared using these operators. And so my copy of K&R has a dog-eared at page 53. So this table comes from page 53 of K&R, and you should have a paper clip or have that folded over for reference. Now the thing to notice is that function and array and these various struct operators have the highest priority, highest precedence, and then that's followed by unary operators. So the star, this is the dereference operator, and then the address of operator. They fall right below the highest precedence operators, and then the binary versions of operators that you use in arithmetic operations are below those. Okay, so just remember that function and array is higher than star. Okay, the dereference. Now the great thing about pointers, although they always seem really complicated, is that there's an algorithm for constructing an English sentence that explains exactly what that definition of the pointer means. Okay, and if you're interested, it's in the K&R in section 5.12. But I'll explain it to you now. Now I don't know how much in this class you're going to remember. Okay, but I guarantee you're going to remember this as the day you finally understood pointers. Okay, all right, so here's how it works. You always start at this is a definition of a pointer of some kind. You always start with the variable name. And then you use your precedence. Then you look for operators on either side of that variable name, and you choose the one that has the highest precedence. Okay, so we start with the variable. So we say p is a, and then we look to the left and the right. There's nothing to the right, but there's a pointer symbol to the left. So we say p is a pointer, and then there's nothing more, and then we always end up with the type of thing that it points at. So p is a pointer to an int. Right, so p is a pointer to some integer in memory. Okay, so we all know that one. That's pretty easy. Okay, what about the next one? You've probably seen something like this. Some programs declare argv using this notation. And so this, you can have an optional size or not. So we start out, we say p is a, well now in this case there's operators to the left and the right. Remember the array operator has higher precedence than the dereferencing operator, the pointer operator. So we say, so p is an array of size 13 of, so there's nothing more, so we go to the left, of pointers. So p is an array 13 of pointers to ints. So p is an array of 13 pointers, each of which points to an int. Right? In this case, p is just the name of the array. So by default, p is the address of the array. When you reference an array name, you're addressing the address of the first element. Okay, how about the next one? Here we're if we put parentheses around things, then we can be explicit. Okay, and this is a good practice. So here we're saying p, and we have to look at this one first because of the parentheses. So p is an array 13 of pointers to ints. So that's the same thing. And here we're just being more explicit. Now what about star star p? So p is a pointer to an int. Okay, so this is a different type of array. So p is a pointer to an int. Okay, and typically, so this is another way to do arrays. So it's the same way that char star points to a string. This can point. It points to a pointer, but then you can index on that. And each one of those then points corresponds to a pointer. Whoops. Okay. Here's another one. Now p, because of the parentheses, we have to go left. So p is a pointer to an array 13 of ints. Okay. So p is a pointer to an array of 13 ints. All right, now what about this one? F is a function or is it a function or a pointer? F is a function, right, because of the precedence. So f is a function returning pointer to int. Okay, so if we go p equal f, then that initializes p to point to some int. All right, and I'm going to do this one. Let's jump down in the interest of time. Totally ridiculous case, just so you can see that this algorithm works.
Let me see if I can get this. So X is an array of 3 elements of pointers to functions that return pointers. I gotta write it down because I'll forget. And I won't be able to validate if I was right or not. So let's do this. So I did read K&R, and I have to agree with him on this, that when I read that section in K&R, I actually, for the first time in my life, fully understood how to parse these expressions. Where before it was just like, first of all, they're intimidating. Just looking at the expression, you're like, what the fuck is going on there? And second of all, I was introduced to this spiral idea, like this spiral system. And that thing is garbage, if you ask me. It just confused me even more. Once you understand the precedence, it's just you go to where the symbol is and you evaluate from the precedence outwards. So X is a 3-element array, or you could rephrase that as an array of 3 elements. We can say 3 pointers to functions that return a pointer to an array of 5 ints. Let's see how accurate I got on that.
Array of pointers. This algorithm works. All right, so X is an array
of
of
3
pointers to functions returning
return
pointers
pointer to an
array 5 of ints.
Of 5 ints.
And if you ever use anything like that in your code, shame on you. All right, so there you go. So that's now you understand pointers, simple as can be, and all you need is page 53 of K&R as a handy reference. All right, so we'll take the last 5 minutes and I'll show you some of the ways you can trip yourself up when you're accessing memory. Okay, so first is the classic scanf bug. You've probably all done this, where you forget to pass it the address of a variable. Instead, you pass it the address. So scanf doesn't know where to put the data. Okay, another common mistake is to read uninitialized memory. So you can't really assume that your heap data is initialized to 0. So here we're mallocating an array of n ints, and then we're going through and we're updating this vector, this y vector. We're taking y, it's yi equal yi plus aij times xj. Okay, so we're assuming that malloc returns memory that's all zeros. So that'll get you. It's also easy to allocate the wrong sized object. So here we want to create an array of n pointers to ints. Okay, and then for each one we want to allocate m ints. Right, so this is we're creating a 2-dimensional array. And can you see the mistake? Which line is buggy? This one? So easy to allocate the wrong size memory that's all zeros. So that'll get you.
Allocating the possibly wrong sized object. So you say malloc n times size of int. Well, p is a pointer to an int. So you want to say n times size of pointer to int on that first line initializing p.
Sized object. So here we want to create an array of n pointers to ints. Okay, and then for each one we want to allocate m ints. Right, so this is we're creating a 2-dimensional array. And can you see the mistake? Which line is buggy? This one? This one or this one? The first one, right? Because we really want size of int star. Right, so we're only incorrectly assuming that ints are the same size as pointers. This is a classic. This assumption is true for 32-bit code. Ints and pointers are the same size, but it's not true for 64-bit. And so this is why when people port 32-bit code to a 64-bit machine, a lot of times it breaks because they have this assumption. Okay, another way it's easy to overwrite memory. So here we're correctly creating this array, but then when we create each of the subarrays, instead of I less than or equal to n, we only created n of these things, but we're traversing n plus 1 because of this less than or equal. So this is a classic off by 1 bug. Okay, another problem you saw it with the code injection attacks from your attack lab, not checking the size of a buffer. So get_s is a classic example of this. So that'll get you into trouble. Another classic size of a buffer. So get_s is a classic example of this. So that'll get you into trouble. Another classic mistake is misunderstanding pointer arithmetic.
Other than size of int instead of just
Then it's incremented by the size of the object that pointer points to. Right? So if you increment an int star by 1, it actually increments it by 4, because that's the size of an int. That's a really important distinction. And so people will often, so here it's assuming that incrementing, so p is a pointer, and the programmer here assumed that he wants to increment the pointer to sort of traverse an array, so he doesn't understand pointer arithmetic. And so to get to the next int, increments p by size of int. Okay, this will really increment it by 16, not by 4. Okay, overwriting memory, that's a really nasty one. And a lot of times this can happen if you don't understand the precedence of the operators that you're working with. So this is a heap, not the kind of heap we've been talking about, but the heap data structure. And this is a function to delete from a heap. And this actually is from my own code, I have to admit. And so I want to delete an element. I want to delete the first element of the heap, right? And then I want to reheapify it. Okay, so and then I want to return that. So I get the first element of the heap. I decrease the size of the heap, or I take the last element and make that the first element. And now I want to decrease the size of the heap, because this delete operation will delete the heap size by 1. So notice here we pass size in as a pointer. And when this function returns, size should be updated. Size is a pointer, the value that it points to should be decremented. Okay, that's our intent. And we do it right here with the size minus minus star. So what we want to do is we want to dereference size.
They're both unary operators.
And then decrement that value. But because the unary minus minus has higher precedence than the dereference, what we're really doing is we're decrementing the pointer and then dereferencing the value that's one word less than our size variable. All right, so these are nasty. And it would have been much cleaner if I had just put parentheses around like I intended, just parentheses, star size parentheses. All right, another way you can mess up is referencing, forgetting the local variables disappear. So if you have a function that returns an address of a local variable, no good. Okay, no good at all. It might be okay for a while until another function reuses that space. It could be a return address. It could be another function's local variable. Another terrible mistake, this is a really bad one, is freeing a block multiple times. Now you know from your understanding now of malloc that free actually writes to the heap, right? It's coalescing, it's changing pointers, it's changing block sizes. So if you free a block that's already been freed, terrible things will happen. Another thing you can do wrong is to reference a block. You forget that you freed a block and then you reference it. So here we free this block X and then we're referencing it here. Another big problem is memory leaks, so failing to free blocks, so allocating some block in a function and then returning, that block will stay there forever, right, because it's garbage. Okay, so there's a number of ways to deal with memory bugs. GDB is sometimes good. At least it'll tell you where a seg fault occurs. And then you got to track down what the write that sort of caused that seg fault. The best thing you can do, but GDB falls down whenever you're doing manipulation of complex data structures. Right? It's just simple sort of looking one instruction at a time. What you really need to do is identify any complex data structure, like a heap, for example, is identifying invariants for that structure that data structure should always maintain. And then you write a function that iterates over that data structure, and checks that all those invariants are true. So for example, in an allocator, one of the invariants is that there should never be two contiguous free blocks. Right? So your consistency checker should go through the heap and make sure there's no contiguous free blocks. Or another invariant is that every free block should be in a free list somewhere. Right? So you would up your consistency checker would scan the heap, count the number of free blocks, and then scan the free list to make sure that the number of blocks in the free list is the same as the number of free blocks. Okay, so this idea of a consistency checker is something you'll use in your malloc lab, but it's also something you should use whenever you're updating any kind of complex data structure. And you know about Valgrind, but the great thing about these heap checkers, okay, I'm passionate about heap checkers, or consistency checkers. The really powerful thing about them is you write them to run silently. They don't print anything unless they find a violation of the invariance. If you write your consistency checker like this, then you can use it like a probe. So your program crashes. So you use this heap checker to do a binary search to isolate the cause. So you put your heap checker here, everything's okay, and then later the program crashes. So now you stick the heap checker here, and now it crashes. The heap checker detects a violation. So you know that the problem is somewhere here, and you can just keep narrowing it down. So it's just like a probe, surgical probe that you can use to track down bugs. And so if you do this, I don't know how anybody debugs malloc without this kind of tool. Okay, so that's it for today. Have a good weekend. We'll see you on Tuesday.
That's like a really good idea. I mean, I do the binary searching type thing, obviously, when I'm debugging, but having these consistency checkers that check your invariants as you're iterating on developing the data structure or algorithm, I think that's like a really clever thing to do. I don't think I've done that before. Like I said, I haven't really developed a bunch of data structures myself, so I guess I haven't had the need for it. It's certainly not novel data structures. But yeah, if you understand the invariance of your data structure and algorithms, just write a program that validates those invariants, and you can like pound define it out of your compile for production, but for development and testing, just have that in there. It doesn't matter if it impacts the performance at all, as long as it's only pound defined for your testing. And then you can run a bunch of tests and verify everything's Gucci. I think I'm gonna use that technique myself. Okay, so we have some reading to do, just to get caught up with the lecture, basically covering the material that he covered. What time is it? We got about an hour remaining, and we have about, let's see, 12 pages to go. Um, 12 pages would be, well, if it's 6 pages, it would be 10 pages. Was it 6 pages would be 1 page every 10 minutes. So I have to do 1 page every 5 minutes to get this done in an hour, which is totally doable. In fact, I have a little 5-minute timer here. I'll just go ahead and use that. All right, first 5 minutes. Explicit free list. The implicit free list provides us with a simple way to introduce some basic allocator concepts. However, because block allocation time is linear in the total number of heap blocks, the implicit free list is not appropriate for a general purpose allocator, although it might be fine for a special purpose allocator where the number of heap blocks is known beforehand to be small. A better approach is to organize the free blocks into some form of explicit data structure, since by definition the body of a free block is not needed by the program. The pointers that implement the data structure can be stored within the bodies of the free block. For example, the heap can be organized as a doubly linked list by including a predecessor and successor pointer in each free block, as shown in figure 948. Using a doubly linked list instead of an implicit free list reduces the first fit allocation time from linear in the total number of blocks to linear in the number of free blocks. However, the time to free a block can be either linear or constant, depending on the policy we choose for ordering the blocks in the free list. So it's a format of heap blocks used for doubly linked free list. So just a typical block like we've seen before, and then when we free it, we just have the predecessor and successor pointers written into the payload section. Using these bits is really clever. I wouldn't have thought of that, I don't think. One approach is to maintain the list in a last in, first out order by inserting, we're on the next page. So let's go ahead and reset. There we go. One approach is to maintain last in, first out order by inserting newly freed blocks at the beginning of the list. With a last in, first out ordering and a first fit placement policy, the allocator inspects the most recently used blocks first. In this case, freeing a block can be performed in constant time. If boundary tags are used, then coalescing can also be performed in constant time. Another approach is to maintain the list in address order, where the address of each block in the list is less than the address of its successor. In this case, freeing a block requires a linear time search to locate the appropriate predecessor The trade-off is that the address order first fits address order is that address ordered first fit enjoys better memory utilization than last in first out ordered first fit, approaching the utilization of best fit. The disadvantage of explicit lists in general is that free blocks must be large enough to contain all the necessary pointers, as well as a header and possibly a footer. This results in a larger minimum block size and increases the potential for internal fragmentation. Segregated free list. So this is the one that he was saying is like really good. As we've seen, an allocator that uses a singly linked list of free blocks requires time linear in a number of free blocks to allocate a block. A popular approach for reducing the allocation time, generally as a segregated storage, is to maintain multiple free lists where each list holds blocks that are roughly the same size. The general idea is to partition the set of all possible block sizes into equivalence classes called size classes. There are many ways to define the size classes. For example, we might partition the block sizes by powers of 2. Or we might assign small blocks to their own size classes and partition large blocks by powers of 2. The allocator maintains an array of free lists with one free list per size class, ordered by increasing size. When the allocator needs a block of size n, it searches the appropriate free list. If it cannot find a block that fits, it searches the next list, and so on. The dynamic storage allocation literature describes dozens of various variants of segregated storage that differ in how they define size classes, when they perform coalescing, when they request additional heap memory from the operating system, whether they allow splitting, and so forth. To give you a sense of what is possible, we will describe 2 of the basic approaches: simple segregated storage and segregated fits. With simple segregated storage, the free list for each size class contains same size blocks. Each the size of the largest element of the size class. For example, if some size class is defined as 17 to 32, then the free list for that class consists entirely of block size 32. To allocate a block of some given size, we check the appropriate free list. If the list is not empty, we simply allocate the first block in its entirety. Free blocks are never split to satisfy allocation requests. If the list is empty, the allocator requests a fixed size chunk of additional memory from the operating system, typically a multiple of the page size, divides the chunk into equal sized blocks, and links the blocks together to form the new free list. To free a block, the allocator simply inserts the block at the front of the appropriate free list. There are a number of advantages to this simple scheme. Allocating and freeing blocks are both fast, constant time operations. Further, the combination of the same size blocks in each chunk, no splitting and no coalescing, means that there's a very little per block memory overhead. Since each chunk has only same size blocks, the size of the allocated block can be inferred from its address. Since there is no coalescing, allocated blocks do not need an allocate free flag in the header. Thus, allocated blocks require no headers, and since there is no coalescing, they do not require any footers either. Since allocate and free operations insert and delete blocks at the beginning of the free list, the list need only be singly linked instead of doubly linked. Okay, we're ahead of schedule here. Let's go ahead and continue reading. The bottom line is that the only required field in any block is a one-word successor in each free block, and thus the minimum block size is only one word. A significant disadvantage is that simple segregated storage is susceptible to internal and external fragmentation. Internal fragmentation is possible because free blocks are never split. Worse, certain reference patterns can cause extreme external fragmentation because free blocks are never coalesced. Describe a reference pattern that results in severe external fragmentation in an allocator based on simple segregated storage. Let's give it a shot. I'll give it a shot. Okay, why are we all the way at that location? That doesn't make sense. Here's one pattern that will cause external fragmentation. The application makes numerous allocations and free requests to the first size class, followed by numerous allocation free requests to the second size class, followed by numerous allocation and free requests to the third size class, and so on. For each size class, the allocator creates a lot of memory that is never reclaimed because the allocator doesn't coalesce, and because the application never requests blocks from that size class again. So I guess I should rephrase this. Allocating and freeing small values, many small values, and then moving on to allocating and freeing many large values. That's kind of what I was getting at with what I said, but of course their answer is more complete than mine. Okay, let's continue reading. Segregated fits. With this approach, the allocator maintains an array of free lists. Each free list is associated with a size class, and it's organized as some kind of explicit or implicit list. Each list contains potentially different size blocks, whose sizes are members of the size class. There are many variants of segregated fits allocators. Here we describe a simple version. To allocate a block, we determine the size class of the request and do a first fit search of the appropriate free list for a block that fits. If we find one, then we optionally split it and insert the fragment into the appropriate free list. If we cannot find a block that fits, then we search the free list for the next larger size class. Repeat until we find, I gotta reset my timer. Repeat until we find a block that fits. If none of the free lists yield a block that fits, then we request additional heap memory from the operating system, allocate the block out of this new heap memory, and place the remainder of the appropriate size class. To free a block, we coalesce and place the result on the appropriate free list. The segregated fit approach is a popular choice with production quality allocators such as the GNU malloc package provided with the C standard library because it is both fast and memory efficient. Search times are reduced because searches are limited to particular parts of the heap instead of the entire heap. Memory utilization can improve because of the interesting fact that a simple first fit search of the segregated free list approximates a best fit search of the entire heap. Buddy systems. A buddy system is a special case of segregated fits where each size class is a power of 2. The basic idea is that given a heap of 2 to the power m words, we maintain a separate free list for each block size to the power k, where k is less than m. Requested block sizes are rounded up to the power of 2. Originally, there was one free block of size 2 to the power m words. To allocate a block of size 2 to the power k, we find the first available block of size 2 to the power j such that k is less than j is less than m. If j is equal to k, then we're done. Otherwise, we recursively split the block in half until j is equal to k. As we perform the splitting, each remaining half, known as the buddy, is placed on the appropriate free list. To free a block of size 2 to the power k, we continue coalescing with the free buddies. When we encounter an allocated buddy, we stop the coalescing. A key fact about buddy systems is that given the address and size of blocks, it's easy to compute the address of its buddy. For example, a block of size 32 bytes with address so-and-so has buddy with the 1 set in the most significant position that's not shared. In other words, the address of a block and its buddy differ in exactly 1 bit position. The major advantage of a buddy system allocator is its fast searching and coalescing. The major disadvantage is that the power of 2 requirement on the block size can cause significant internal fragmentation. For this reason, buddy system allocators are not appropriate for general purpose workloads. However, for certain application specific workloads where the block sizes are known in advance to be powers of 2, buddy system allocators have a certain appeal. Garbage collection. With an explicit allocator such as the C malloc package, the application allocates and frees heap blocks by making calls to malloc and free. It is an application responsibility to free any allocated blocks it no longer needs. Boop. Failing to free allocated blocks is common programming error. For example, consider the following C function that allocates a block of temporary storage as part of its processing. So we got garbage, malloc, and they return nothing. So we never free it. Since P is no longer needed by the program, it should have been freed before garbage returned. Unfortunately, the program has forgotten to free the block. It remains allocated for the lifetime of the program, needlessly occupying heap space that could be used to satisfy subsequent allocation requests. A garbage collector is a dynamic storage allocator that automatically frees allocated blocks that are no longer needed by the program. Such blocks are known as garbage, hence the term garbage collector. The process of automatically reclaiming heap store is known as garbage collection. In a system that supports garbage collection, applications explicitly allocate heap blocks, but never explicitly free them. In the context of a C program, the application calls malloc, but never calls free. Instead, the garbage collector periodically identifies the garbage blocks and makes appropriate calls to free to place those blocks back on the free list. Garbage collection dates back to Lisp systems developed by John McCarthy at MIT. Is that guy, one guy? I think he's kind of like a thin face, a thin beard, glasses, like really weird hair. Yeah, this guy. The glasses dude. I remember him having a thinner face than that. I gotta learn about him. Is he still alive? No. He passed away. He was an OG though. Father of AI and Lisp, dies at 84. Still rocking those glasses, man. I mean, 2008, when did he pass away? What if he told him he had 3 years to live when he was this old? If he would change his diet or anything. What did he pass away from? I just hate to see people succumb to obesity, especially great minds. I mean, we all have our time when we have to leave this planet. Shit. I'm far behind on my reading here. It is an important part of modern language systems such as Java, Perl, ML, Perl, and Mathematica, and it remains an active and important area of research. The literature describes an amazing number of approaches for garbage collection. We will limit our discussion to McCarthy's original mark and sweep algorithm, which is interesting because it can be built on top of an existing malloc package to provide garbage collection for C and C++ programs. Interesting. Garbage collector basics. A garbage collector views memory as a directed reachability graph of the form shown in figure 949. Okay, the nodes of the graph are partitioned into a set of root nodes and a set of heap nodes. Each node corresponds to an allocated block in the heap. A directed edge P to Q means that some location in block P points to some location in block Q. Root nodes correspond to locations not in the heap that contain pointers into the heap. These locations can be registers, variables on the stack, or global variables in the read-write data area of the virtual memory. We say that node P is reachable if there exists a direct path from any root node to P. At any point in time, the unreachable nodes correspond to garbage that can never be used again by the application. The role of a garbage collector is to maintain some representation of the reachability graph. and periodically reclaim the unreachable nodes by freeing them and returning them to the free list. Finished it on time. Okay, so we got a garbage collector view of memory as a directed graph. We got our root nodes, our heap nodes, we got our little cycles, and they're completely unreachable, and you got nodes that are unreachable. Integrating a conservative garbage collector into C malloc package. So your C application program calls into malloc. It calls into conservative garbage collector that then curls free. Huh. Okay, we get into that in a little while here. Garbage collectors for languages like ML and Java, which exert tight control over how applications create and use pointers, can maintain an exact representation of the reachability graph, and thus can reclaim all garbage. However, collectors for languages like C and C++ cannot in general maintain exact representations of the reachability graph. Such collectors are known as conservative garbage collectors. They are conservative in a sense that each reachable block is correctly identified as reachable, while some unreachable nodes might be incorrectly identified as reachable. Collectors can provide their service on demand, or they can run as separate threads in parallel with the application, continuously updating the reachability graph and reclaiming garbage. For example, consider how we might incorporate a conservative collector for C programs into an existing malloc package, as shown in figure 950. The application calls malloc in the usual manner whenever it needs heap space. If malloc is unable to find a free block that fits, then it calls the garbage collector in hopes of reclaiming some garbage to the free list. The collector identifies the garbage block and wait, I gotta rewind here. The application calls malloc in a usual manner whenever it needs a heap space. If malloc is unable to free a block that fits, then it calls the garbage collector in hopes of reclaiming some garbage to the free list. The collector identifies the garbage blocks and returns them to the heap by calling free function. The key ID is that the collector calls free instead of the application. When the call to the collector runs, malloc tries again to find a free block that fits. If that fails, then it can ask operations for additional memory. Eventually, malloc returns a pointer to the requested block if successful, or a null pointer if unsuccessful. So this works in a single-threaded allocator, where you're calling malloc, and the garbage collector can then walk its stack looking for pointers and values, like root values, and look at the registers and everything. But it can only do that for the thread that's calling into malloc. If there's other threads calling into malloc or not calling into malloc that you handed off a pointer to, like say we got a pointer in thread A that was stored on the stack, or say we stored it in a global, and then thread B came by, read the global, set it to 0, so the garbage collector will not be able to find the pointer there. Now thread B has a pointer on its stack that points into the block that was allocated by thread A, and now thread A goes in to allocate something else, and the garbage collector runs. It's going to traverse from global variables, registers, and thread A stack, but it's not going to be able to find the reference in thread B's stack. Mark and sweep garbage collectors. A mark and sweep garbage collector consists of a mark phase, which marks a reachable and allocated descendants of the root nodes, followed by a sweep phase, which frees each unmarked allocated block. Typically, one of the spare low-order bits in the block header is used to indicate whether a block is marked or not. Our description of mark and sweep will presume the following functions, where PTR is defined as typedef void PTR. So we got is PTR, if P points to some word in allocated block, to return pointer B to the beginning of that block returns null otherwise. Let's reset our counter here. Okay. Block marked, block allocated, mark block length, unmarked next block. I don't really want to go over the details of this, to be honest. It's not something that they go into further detail on. Alright, the mark phase calls the mark function shown in figure 951 once for each root node. The mark function returns immediately if P does not point to each root node. Sorry, does not point to an allocated and unmarked heap block. I guess if you're going from root nodes and you have the stack pointer of every, I guess you could do it from the base of this thread stack, right? Problem is you don't know when the stack ends without reading the stack pointer. You can't just read the stack pointer of another thread. You have to have something on the stack that indicates that that's the current stack frame, and there isn't something like that in the C calling convention. So I don't see a way of doing it. Anyways, otherwise it marks the block and calls itself recursively on each word in block. Each call to the mark function marks any unmarkable and unreachable descendants as of some root node. At the end of the mark phase, any allocated block that is not marked is guaranteed to be unreachable and hence garbage that can be reclaimed in a sweep phase. Sweep phase is a single call to the sweep function shown in figure 951b. The sweep function iterates over each block of the heap, freeing any unmarked allocated blocks that it encounters. Figure 952 shows a graphical interpretation of mark and sweep for a small heap. Block boundaries are indicated by heavy lines. Each square corresponds to a word of memory. Each block has a one-word header, which is either marked or unmarked. Okay. I feel like we're getting close here. Initially, the heap in figure 952 consists of 6 allocated blocks, each of which is unmarked. Block 3 contains a pointer to block 1. Block 4 contains pointers to blocks 3 and 6. The root points to block 4. After the mark phase, blocks 1, 3, 4, and 6 are marked because they are reachable from the root. Blocks 2 and 5 are unmarked because they are unreachable. After the sweep phase, the 2 unreachable blocks are reclaimed to the free list. Conservative mark and sweep for C programs. Mark and sweep is an appropriate approach for garbage collecting C programs because it works in place without moving any blocks. However, the C language poses some interesting challenges for the implementation of the isPointer function. First, C does not tag memory locations with any type of information. Thus, there is no obvious way for isPointer to determine if its input parameter P is a pointer or not. Second, even if we were to know that P was a pointer, there would be no obvious way for isPointer to determine whether P points to some location in the payload of an allocated block. One solution to the latter problem is to maintain a set of allocated blocks as a balanced binary tree that maintains the invariant that all blocks in the left subtree are located at smaller addresses and all blocks to the right subtree are located at larger addresses, as shown in figure 953. This requires 2 additional fields left and right in the header of each allocated block. Each field points to the header of some allocated block. The isPointer function uses the tree to perform a binary search of the allocated blocks. At each step, it relies on the size of the field of the block header to determine if P falls within the extent of the block. The balanced tree approach is correct in the sense that it guarantees to mark all of the nodes that are reachable from the roots. This is a necessary guarantee, as application users would certainly not appreciate having their allocated blocks prematurely returned to the free list. However, it is conservative in the sense that it may incorrectly mark blocks that are actually unreachable, and thus it may fail to free some garbage. While this does not affect the correctness of application programs, it can result in unnecessarily external fragmentation. The fundamental reason that mark and sweep collectors for C programs must be conservative is that the C language does not tag memory locations with type information. Thus, scalars like ints or floats can masquerade as pointers. For example, suppose that some unreachable allocated block contains an int in its payload whose value happens to correspond to an address in the payload of some other allocated block B. There's no way for the collector to infer that the data is really an int and not a pointer. Therefore, the allocator must conservatively mark block B as reachable, when in fact it might not be. Common memory-related bugs in C programs. Managing and using virtual memory can be a difficult and error-prone task for C programmers. Memory-related bugs are among the most frightening because they often manifest themselves at a distance, in both time and space, from the source of the bug. Write the wrong data to the wrong location, and your program can run for hours before it finally fails in some distant part of the program. We conclude our discussion of virtual memory with a look at some of the common memory-related bugs. Dereferencing bad pointers. As we learned in section 972, there are large holes in the virtual address space of a process that are not mapped to any meaningful data. If we attempt to dereference a pointer into one of these holes, the operating system will terminate our program with a segmentation exception. Also, some areas of virtual memory are read-only. Attempting to write to one of these areas terminates the program with a protection exception. A common example of dereferencing a bad pointer is the classic scanf bug. Suppose we want to use scanf to read an integer for standard in into a variable. The correct way to do this is to pass scanf a format string and an address of the variable. However, it is easy for new C programmers, and experienced ones too, to pass the contents of val instead of its address. In this case, scanf will interpret the contents of val as an address and attempt to write a word to that location. In the best case, the program terminates immediately with an exception. In the worst case, the contents of val correspond to some valid read-write area of virtual memory, and we overwrite memory, usually with disastrous and baffling consequences much later. Reading uninitialized memory. While BSS memory locations, such as uninitialized global C variables, are always initialized to 0 by the loader, this is not true for heap memory. A common error is to assume that heap memory is initialized to 0. So we got matrix vector, so it's a pointer to ints. So it might be a two-dimensional array, or it might be a one-dimensional array that we're passing a pointer to. Then we get an int star x and int n. So we call malloc n size of int. We're reading from we're doing a plus equals, assuming it's 0, so it could be anything. In this example, the program has incorrectly assumed that vector y has been initialized to 0. The correct implementation would explicitly 0 y sub I, or use calloc. Allowing stack buffer overflows. As we saw in section 310.3, a program has a buffer overflow bug if it writes to the target buffer on the stack without examining the size of the input string. For example, the following function has a buffer overflow bug because the gets function copies an arbitrary length string to the buffer. To fix this, we would need to use the fgets function, which limits the size of the input string. We already did a lab on that whole thing. Okay, we got, what, 3.5 pages on these things. These are fun though. Assuming that pointers and objects they point to are the same. One common mistake is assume that pointers to objects are the same as size as the objects they point to. The intent here is to create an array of n pointers, each of which points to an array of m ints. However, because the program has written size of int instead of size of int star, in line 5, the code actually creates an array of ints. The code will run fine on machines where ints and pointers to ints are the same size, but if you run this code on a machine like a Core i7 where a pointer is larger than an int, then the loop in line 7 to 8 will write past the end of the A array. Since one of those words will likely be the boundary tag footer for the allocated block, we may not discover the error until we free the block much later in the program, at which point the coalescing code in the allocator will fail dramatically and for no apparent reason. This is an insidious example of the kind of action at a distance that is so typical of memory-related program bugs. Making off by one errors. Off by one errors are another common source of overriding bugs. So we got a make array 2, it's like a 2-dimensional array. We malloc up n times the size of an int pointer. And then for each of those, we malloc up m times the size of an int, thing that we're pointing at. But we got an equal sign here. That's the problem there. I saw something where like on the web you can make this thing like so infinitesimally small you can't even see it. Or you can use like a span and just hide it. And then when people copy your code, even though it says less than, they copy it and they get a less than or equal. So you can do malicious things that way. There's another version of the program in the previous section. Here we have created an element array of pointers in line 5, but then tried to initialize n plus 1 of its array elements in lines 7 and 8, in the process of overriding some memory that follows the A array. Referencing a pointer instead of an object it points to. If we're not careful about precedence and associativity of C operators, then we incorrectly manipulate a pointer instead of the object it points to. For example, consider the following function, whose purpose is to remove the first item in a binary heap of pointer size items, and then reheapify the remaining size minus 1 items. And it's because the equals is a higher precedence. So if we just search for C precedence, sorry, the minus operator is higher precedence than the dereference. I think that's the bug. Can I just get the fucking table, please? Thank you. Where's the minus up here, higher than the unary operator, because it's right to left. They're the same level of precedence, but these unary operators are evaluated right to left instead of left to right. That's why when you have star, yeah, yeah. Unary operators evaluate right to left, along with ternary operator, assignment operator, obviously, and like just those three. Okie dokie artichoke. Let's continue on. In line 6, the intent is to decrement the integer value pointed to by size pointer. However, because the unary and star operators have the same precedence and associate from right to left, the code in line 6 actually decrements the pointer itself instead of the integer value that it points to. If we are lucky, the program will crash immediately, but more likely we will be left scratching our heads when the program produces an incorrect answer much later in its execution. The moral here is that the parentheses whenever in doubt, use parentheses whenever in doubt about precedence and associativity. For example, in line 6, we should have clearly stated our intent by using the expression star size inside of parentheses minus minus. Misunderstanding pointer arithmetic. Another common mistake is to forget that arithmetic operations on pointers are performed on units that are of the size of the objects they point to, which are not necessarily bytes. For example, the intent of the following function is to scan an array of ints. Scan an array of ints and return a pointer to the first occurrence of val. So we have our int star p, which is our array. We have our value that we're searching for. We return a pointer to that location. So while dereferencing p has a value and the value is not equal to the value that we're searching for, then we increment p, but it should be p plus plus. However, because the line 4 increments the pointer by 4, the number of bytes in an integer each time through the loop, the function incorrectly scans every 4th integer in the array. Here we go. Referencing non-existent variables. Naive C programmers who do not understand the stack discipline will sometimes reference local variables that are no longer valid, as in the following example. This function returns a pointer, say, p to local variable on the stack and then pops its stack frame. Although p points to a valid memory address, it no longer points to a valid variable. When other functions are called later in the program, the memory will be reused for their stack frames later. If the program assigns some value to p, then it might actually be modifying an entry in another function's stack frame with potentially disastrous and baffling consequences. Reference data in free heap blocks. A similar error is to reference data in heap blocks that have already been freed. It's a use after free bug. Consider the following example which allocates an integer array x in line 6 and prematurely frees block x in line 10, and then later references it in line 14. So we got our allocation into x, and then we do it into y, and then we read from x. Depending on the pattern of malloc and free calls that occur between line 6 and 10, when the program references xi, line 14, the array might be part of some other allocated heap block and may have been overwritten. As with many memory-related bugs, the error will only become evident later in the program when we notice that values in y are corrupted. Introducing memory leaks. Memory leaks are slow, silent killers that occur when programs inadvertently create garbage in the heap by forgetting to free allocated blocks. For example, the following function allocates a heap block x and then returns it without freeing it. If leak is called frequently, then the heap will gradually fill up with garbage, in the worst case consuming the entire virtual address space. Memory leaks are particularly serious for programs such as daemons and servers, which by definition never terminate. Summary: virtual memory is an abstraction of main memory. Processors that support virtual memory reference main memory using a form of indirection known as virtual addressing. The processor generates a virtual address, which is translated into a physical address before being sent to the main memory. The translation of address from a virtual address space to a physical address space requires close cooperation between hardware and software. Dedicated hardware translates virtual addresses using page tables whose content are supplied